I'm going to talk about deep learning. Deep learning seems to be has been a topic recently, which become a tool for many applications or scientific computing. However, it seems that the mathematical theory behind this deep learning is still lagged behind. So there are many ways to look at the deep learning. Today, I'm going to look at the deep learning from the approximation angle. And I will start, why I look at this angle, because deep learning, especially for supervised learning, for other tasks of the deep learning, is explicitly or implicitly, it's about approximation of function. Especially like supervised learning is like a regression, and essentially it is an approximation to a function. So I will start with a very brief introduction of the approximation theory and link that to the deep learning. And the key difference from the deep learning approximation of the deep learning and the classical approximation is, for the deep learning, the approximation is approximation of the function by compositions. By composition, many layers of compositions of a function. So I will, in the second part, I will talk about this. And then the third part, this part is very technical, but it's very important. It's given a deep neural network and people talk about architecture. I think the basic architecture is a activating function, depth, and width of the neural network. Then I will start for this section essentially for ReLU, and I also have other section, the activating function, the approximation exactly in terms of the width and the depth. And finally, I will talk about a universal property, universal approximation property. Okay, universal approximation property is a very common kind of terminology in deep learning. Essentially say you can approximate a function as close as you want to. That's called universal approximation property. But so far all the results essentially about when your number of neurons go to infinity. That's even for classical approximation. Your number for the generator will go to infinity if you want to absolutely close to a function, arbitrarily close to a function. But here we design an activating function, a very simple computable activating function, which can design a neural network with a finite number of neurons, which can achieve the universal approximation property. That means the hypothesis space by finite depth and width. This hypothesis space can be dense in the space of a continuous function. That was a very surprising result, but I'm going to, this is a very recent new results. I'm going to talk about that in the last. Okay, let's start with from the approximation. And approximation theory, I guess, idea is very simple. You have a function, given a function f, it's not available or it's so complex. You want to use a simple function g. Okay, you want a single function g to approximate. The g is simple because it's computables, for example. So for to approximate, this epsilon is your error bound. Okay, you want to then with approximation within some distance you define. Normally the function space norm, LP or L infinity, P can be 1 to infinity. So F is from RD to R, G can be Rn to R. So G can be very simple and it can be like a linear. So you can think about if this approximation makes sense, even for D equal to N equal to 1, that essentially if you G choose such a simple function, you want to have a line to approximate a curve, you want to make it a sense or make it a good approximation, you have to have a T. Okay, the map T, which from RD to Rn, such that G composed with T can close to F as you wish. I think if we put in this format, all the approximation can put into the same form, one format. For example, in the classical approximation, the T essentially is a given, which is independent of your function F, and also independent independent your data, but it's dependent on N, epsilon. Okay, it's N is dependent on your epsilon. That's your traditional approximation is like that. Okay, so this is then for the classical learning, also or you may call shallow learning. They move a little more. Your T can be learned, but you basically parameterize the T, but they only use a few parameters. Okay, very few parameters. So deep learning, you are really further decompose T to many layers. Each layer becomes simple and completely parameterized, so that you learn T with a huge number of the parameters. Okay, okay, but this is good in the some sense. Your N is independent of epsilon. Okay. All right, let's look at classical approximation. Classical approximation, you have two widely used. One is the linear approximation. Linear approximation essentially give a generator N. Okay, you can give a generator N. Then the linear approximation is either projection or interpolation, or either semi-projection or quasi interpolation. Okay, so that's what I normally do. Okay, what do you need for this linear approximation? You want to have when N is bigger, your generator become big. If your generator become bigger, you're going to have a good approximation with N go to infinity essentially. Then you need to have your coefficient AGA should decay fast, so to get a good approximation. So in most cases, those AGA either you either say in the Hilbert space or in the AGA is some canonical coefficients. Those coefficients you want to decay fast, you need the smoothness of the function. So for all the classical approximation theory, you always start with when F has a certain smoothness. Okay, you have a smoother function, you have a better approximation. Okay, that's the classical approximation. Then another one is now is also classical, but they call n-term approximation. N-term approximation, what's the difference between the linear approximation? You have a bigger dictionary, D, to start from. See, D is huge. However, your T is like that. So then your G, you give the budget. Your A, the coefficient A sequence only have n term, non-zero n term. Only have n non-zero terms. Okay, so that's what you have a budget. Basically, you're only allowed to use n. This is called n-term approximation. So which is first of all, this is not linear because because of the sum of the best approximation is not the best approximation of the sum. Okay, so it's not linear. However, the advantage for that is because in some sense you order for each given f, you order the basis. So this decay rate of the coefficient can be less. So therefore, this one can approximate well for piecewise smooth function instead of smooth function. And in fact, wavelet approximation is essentially based on this n-term approximation. Okay, and that is also why wavelets are widely used for imaging, compression, and restoration, because imaging are piecewise smooth. In fact, they are piecewise constants. Also, all the sparsity-based approximation and compression sensing, the underlying approximation theory is n-term based approximation. I made my career in last 20 years work on that, and until I see the deep learning, now I'm more focused on the deep learning. So what's the deep learning is? So deep learning is actually, okay, you are given hypothesis space, which is, as I said, highly parameterized space. Each function is get a function set or a manifold in the function space. You have phi x zeta. Okay, theta is for given theta is a function. You can find. So this function, as I said, they are well organized by composition. Okay, you have a G that's essentially in the neural network. This is the outcome layer. This is a T. T T can be further decomposed to the air level. Okay, air level. That's the latent hidden layer. Okay, so your each Ti is a composition of the two functions. One is alpha and function. Alpha is W is your matrix, and B is the vector. So your air is actually depth. Your loads, number of loads of W is your width of the neural network. Okay, so sigma is an activating function. I will give you a few examples of activating functions later. But it's a univariate function. So your sigma, then after that you compose H with a sigma. You act on the component wise, you get a Tj plus 1. Okay, so that means, okay, each Tj is completely parameterized. So you have a huge number of the parameters. That's what you have. Okay, this is the income layer. This is all the hidden layer. This is the outcome layer. Okay, this is your network. Okay, for simplicity, we will make all the widths the same. Then you have width n, your depth is L. Okay. Okay, so for the approximation concern, okay, you need to have a distance. Okay, point-wise distance, you have a distance L, define L. Then you define L, you depend on your distribution of your data. Then you have a L1 basically norm over that, of the distance function essentially. Okay, so this is the arrow. Okay, that means that you choose the arrow. So this, if you take a simple case, L is your Euclid norm and U is the uniform distribution. That is your really normal L2 norm of a function. Okay, but deep learning, theoretically, deep learning is you want to, in your hypothesis space for given L, given L and N, you want to find the theta. This is a set of parameters. Which so this distance, this arrow become a minimum. This arrow, the minimized arrow, is exactly your approximation arrow. Okay, that's the approximation arrow you want to find, you want to estimate. Okay, so all my talk essentially to talk about how to estimate this arrow. But practically in machine learning, you don't have a function available. Sometimes you even don't know the distribution for the data. So practically you cannot do for the computation wise, you cannot do the system minimization. So what do? You have a given data, given sample, instead of using a system risk function that I call best risk function, you're using the empirical risk function. That's the given by data. Okay, so then to this we call this model, this approximation model, or this empirical model. For this model, this is computable now. You're computable. You want to find the goal for deep learning is essentially practically you are do the computation of the data such that this cost function, this empirical risk reach to the minimum. Okay, that's the empirical model. Then, but practically, this minimization is a huge dimension of a non-convex. So at the end, even convex, you don't have a exact theta S minimizer. you only have a numerical solution. For the numerical solution, you at the end, really what your error you want to estimate when you do all the computing, you want to know the this error. Okay, this is the practical you want to know. But for this error is sum of the 3 errors. This one is a approximation error. This one is basically your numerical solution and this with the min model. This is called optimization error. And this one is a generalization error. That's the terminology used by the machine learning community. But I like to say this is exactly the model error. Okay, between the best model and the empirical model. Okay, this is the model error. Okay, now your really computational error is the sum of these 3 errors. Okay, first of all, approximation error is important. If I don't have this approximation error, even you have a small computational error and a generalization error, you only can conclude you can approximate function where if the function is in the hypothesis space. Only you bound the distance from your target function to the function to the hypothesis space. This approximation error, then you kind of know that well. Okay, so this optimization error. Of course, I said that and the generalization error. This is the community of the optimization people, but it's very difficult. It's an unconvex problem, and the generalization error is essentially many. If you know that the statistician work on that, it's called statistical machine learning. Many of the paper is on generalization error, basically error between the 2 models. Okay, this talk I'm not going to talk about optimization error, and I'm not going to talk about generalization error. I'm only talk about the approximation error. All these 3 errors, none of them are easy to do. Okay, now let me say why. Because optimization error is non-convex and high dimension. Generalization error, because your parameter is so big. Okay, so since the parameter number is so big, it's a traditional method may not work because traditional results normally, and the numerator is the dimension of the parameter. In the denominator is the number of data. Now your dimensional parameter is bigger than data, number of data. So that's the problem. Okay, but among those is so the optimization error and the generalization error depend on the algorithm, depend on your model, depend on your data. But my approximation error does not depend on data, does not depend on your model. It depends only on your mathematical analysis. I think among those 3, approximation error is still the simplest one. So I take the easy job and I focus on the approximation error. To summarize, you have a target function, and you have a hypothesis space. The hypothesis space is highly parameterized, and you want to find the amount of hypotheses that give for a given distance. You want to have a function which have the best approximation. Okay, so this one normally you have because your best approximation is of minimization, you have a numerical algorithm to compute it. That's the finally computer this set. It's called the learning model. That means learn the parameter. This learning model, you have a tool. Your problem is optimization problem. So that's you have a learning model. You have optimization error because this may not be the main method. Most time it is not. But this your minimization is not from your best model, it's from an empirical model because you only have a data, so you have another error. This is the generalization error. Okay, so this talk is focused on this approximation error. Okay, now we will talk about the approximation error. We look at what's the idea? Okay, what's the basic ideas we are using for our analysis, and what's the key difference between the classical and what we are doing now? Okay, in the classical approximation, basically, essentially for all the approximation theory, doesn't matter you are working with which area, finite maths or a spline or whatever, key ingredients for classical approximation are following 2 key ingredients. First, locally reproducing polynomial. Secondly, smoothness of the function. Locally reproducible polynomial up to a certain degree, then your smoothness have to match with this degree. Okay, smoothness order have to match with the degree. What do? You have a smoothness, you do the local Taylor expansion. Once you do the local Taylor expansion, because the first, since all the polynomial can be reproduced up to that degree, then you only have a remainder term. So you remainder term, then your approximation key is step aside. That's why you always subdivide the domain. That's always, that's fundamental. So this I call local approach. Then you think about why should I do that? Why not I should divide the range? Divide the range, if I range to a small ball, if you range to the small ball, like a BI, then your approximation, as long as your range cut to the small enough, your approximation automatically have. So the problem is that your inverse of this small ball for the range become a complex. Okay, so that's the problem. So somehow, what do? We use the map T to simplify that. That's what the composition are working for that. So you think about that. Okay, for the classical operation, the good function are smooth function, but for this one, for this now for the deep learning, good function in some sense your level set should be good. Okay, this is the non-local approach I call. Look at that. If you think carefully, Riemann integration basic idea is local approach because you divided the domain. Okay, if you do the imaging, TV method, waved method, most of them are local approach. But the bigger integration, you think about it is global approach. It's non-local and also non-local TV. Non-local, if you think of probability, and basically is non-local, but they only need to know the volume of the F inverse BI. But now we are needed to know more than that. Okay, we are more complex. Okay, so key difference, that's a different approach. Okay. Okay, so now forget about the deep neural network. We talk about the mathematics. Now we want to talk about approximation by composition of the function. But what is the mathematics behind? We forget, even we don't think about a neural network. Okay, look at the setting. Well, now we have a data. You have a data. You want to have T and G. You have to, so such that the G composed with T have a good robust approximation. Okay, so what is the mathematics behind this? Okay, so what kind of mathematics question we can ask? The first question we maybe ask that for given F and G, okay, G can be more complex than linear. Is there a measurable function T such that F can be G composed with T? Okay, the answer is yes. Okay, we can prove that the condition is not very strong. You just need an image for G. Of course, you need an image it will compose contain image of F. If you don't have that, of course you cannot approximate F because this is clear. Okay, if your G is constant, say your F unless F is constant, you cannot approximate. Okay, and G is continuous, but G is continuous even this condition we can weaken. Okay, but I don't go too much. Then they always exist. Okay, these exist. This is equal to that. The problem is that this theorem is nice, but the problem is that the result of the T is not constructed. Okay, we can prove existence, but we cannot construct it. So mathematically good, but if we cannot construct it, then I go one step back. I say, okay, given the error bound epsilon, can I really construct a measurable function T so that that you can do? Okay. That's in fact you just need this condition, you can do that. Okay, in fact you gave me F, give me epsilon, I can write G out. Okay, this is a constructive proof. Okay, proof. Okay, but this is a constructive proof you can write out. Of course, the next question is if I give you data only, can you make it decompose to the further t to the few HTI to become simple, and you can learn TI. I have an algorithm to learn and to that get a good approximation. Okay, we do have a theory, do have a method algorithm to so that you can get to that. Okay, the algorithm in fact is simple. Okay, I don't go bother this algorithm too much to use. This algorithm divided to the 3 steps. It's iterative. First, each step you identify the bad approximation point. That's like you build a small network. Okay, to kind of like a small classification, good approximation or bad approximation. For the bad one, you improve. You learn again. Basically, you learn again to improve the approximation. Then you update. You go continue. Okay, that's what it is. So this is a procedure, and you may think, okay, this is a procedure. You look at it, it's really very systematic. We can prove it is very systematic. But you may have a question. Question is when you stop. You know, we have a stop criteria. This is the arrow at the k+1 level, L+1. This is the arrow of L. So the arrow of the L+1 iteration is the arrow of the L's iteration multiplies the number. This is all the RAP and the number. We have a mathematical mean for that. Also, moreover, we can estimate this RAP in each iteration. So you estimate all the number. If this number is smaller than 1, you can continue. If the one bigger than 1, you stop. Okay, that's what I did. Okay, we did have a numeric simulation for like a fashion MNIST, and also this data fitting. Results is good. Okay, of course, this is a fashion MNIST or MNIST. All these are very well established state of arts algorithm for deep learning. We are not going to claim that we are beat them, but the key here is our algorithm doesn't work. The proof of concept it doesn't work. Also, we use a very small net can reach to the same accuracy. Okay, the net can only have a 3 or 4 layer kind of depth, and the width is also not very 32 or something like that. Okay. Okay, this is about mathematics. Then you may ask, okay, so that's your mathematics. Okay, but whether any neural network can follow what you establish there. Okay, we look at the one very nice widely used neural network called residual nets. Okay. Residual nets, you can this is the XK. This is basically XK plus this one. This H is the H essentially generated by your ReLU and your essentially W and BK. That's exactly each layer of your neural network. Okay. So this is a discrete. Of course, this real neural network. You can continuous time idealization become a ODE, dynamic system. Okay, it becomes this one, your H, then you have a control family. The control family is for the H is of course from a activating function, and this is a format. Okay, form. You have parameter like that. This is the control family. So okay, this procedure is not our discover. Okay, people use it for the stochastic gradient descent method. Okay, so but we are the first using this to investigate the approximation power for these residual nets. Okay, now how to link that? This x, this differential equation for x. If you put x0 to x, your x tau, the end point is the dynamic system end point is your xt. This tau t is your flow map. Okay, it's a flow map from x0 to tx. Okay, that's exactly the t. This residual net is this you can make the t. So once you have a t, you can life become much simple. Our all the previous results fitting. If you participate the domain 0 to tau time domain to the unit, then it become HTGA define that your t is really become a composition of these layers. If you make time, this partition become a final, your t can be very simple, close to identity even. That's all the theory guarantee that. Okay, that's looks beautiful. But the next question is that, key question you want to ask is what kind of control family and what kind of control family you want to have such that this can guarantee your G composed with T have a good approximation. That's what we want to know. So we have a theorem. Theorem is here. Okay. First of all, you have to have this one is exactly the same as the image. If G, you have to compare image of F. That's for sure. You need F. You don't have a then F. I claim that my control family or the activating function only need to satisfy some very mild condition. With the mild condition, we can prove for actually for P between 1 to infinity, not including infinity, sorry about that. And for actual epsilon, there exists of T such that flow map. Such as small ellipse. This is UAP. This is exactly we prove the UAP for the, if we make the discretization back to the discrete case, we get the UAP, universal approximation property for residual nets. That's the first time people prove it. Okay. This is more like a pure math paper. So that's why it's published in the Journal for European Mathematical Society. So, but the results, implication is clear. We prove the UAP for residual nets. Okay, why I say condition is minor? Minor because the most of activating function people use it. One is the ReLU, that's the piecewise linear. This is the sigma. This is also the tongue. Okay, all the okay. Normally, all the activating function people can use all kind of activation. People like the activation like that. Okay, at the beginning you are calm, then you switch on, then you keep on that. Okay, ReLU is not good. ReLU is something you keep quiet, then switch on, you go forever. But you know that two linear combination of ReLU, you kind of quiet, switch on, then keep on the level. Okay, people have a reason they like this shape, but I have a simple reason because like I gave a talk. This is like more like your neural. When my talk is boring, you are sleeping, your neural is sleeping. I get something exciting, you need to switch on. Then if I keep doing good job, yes, then maybe you could be kicked back. Okay, that's why people like this kind of shape of the activating function. Why I say my condition is mild because all these like ReLU, you get the residual nets satisfy my condition. You have all these other these two functions also satisfy my condition. Furthermore, okay, normally people do the residual nets, they don't do the update each layer. They have a blockwise update. So this block structure also satisfies my condition. So that means all those kind of residual nets satisfy my condition and they have a UAP. Okay. Okay, now I go back, come to the points to how about the approximation rate in terms of width and depth. Let's start with the ReLU. Okay, this set of results, the first set of results are for ReLU. Okay, for given width n and the depth L. That's n essentially is a key parameter for your width, and L is for the depth. Can I have an approximation order in terms of n and L? Yes, if I have a Lipschitz function, okay, then I have this if we have a Lipschitz function, I have the n and L in this way. Okay, I know exactly size of the L neural network. I get at the rate. Okay, that's n square L square. But we still have a d here. Okay, so I have a log n. Okay, this result is optimal in the sense this is also a lower bound. So you have no way to improve. Okay, so upper bound also lower bound. Okay. Also, this result, of course, this is for Lipschitz, but we know that we can get the result for continuous in module in terms of module continuity. So, but I don't go to details. The results is essentially the same. So look at the history. What is the history? Okay, for n L equal to 1, that's the one hidden layer. For L equal to 1, in fact, for D equal to 1, we know this is the result. Okay, this is the result. For the d bigger than 1, we know that this result will not be at most have a this rate, but no proof for d equal to bigger than 1 have a this rate. Okay, there are no proof. I ask many people, nobody know the literature. People claim that, but no proof in the literature, and I don't know how to prove it. But for L equal to 1, okay, for the Euroscape, our first paper is also published written in the same time, but the Euroscape before us. What the Euroscape proves? Euroscape proves that when d n width equal to 2d plus 10, then your L sufficiently large. This is the asymptotic analysis. Asymptotic L sufficiently large, you have a this rate. Okay. Our final results, of course, our final result is the key difference is where for any n L you have a system result. Okay. Also, it's not asymptotic. It's exactly characterized by in terms of n and L. So all the difficulties are how do you calculate the exactly approximation error, not asymptotic analysis. But asymptotic, in some sense, to me, like you ask you build a building, have a infinite budget. But for me, I need a system within the budget to reach to that. Okay, this is all the technical because we need to do the exact estimate in terms of n and L. Okay, so this is we have a series paper. I think number 1 is the final result. I think for this results get to the best. I think this is the number 1 paper. But we developed a long time from number 3 to number 2 until number 1. Okay. Okay. So this results also optimal in a sense. You have no way to improve, but people don't like it because people don't like it because you have a d, you have a 1 over d here. Okay, because people don't like that. If you don't like that, what you can do? You cannot do much because if you want to stick on the Lipschitz or continuous, that's all the best result you can get. So only choice you can have is either you make a function space become smaller. That's if you do that, look at that. Okay, if I make a function space are so small to the like polynomial space. Okay, so if I look at polynomial space, results is very encouraged. You can have a easy results. Okay, you have a polynomial space. You can if you have the polynomial of degree k, you essentially have this n to the power negative L. That really shows the power of the composition. You are getting encouraged because you see your approximation when you with the composition, you are very good. It's very good. Okay, for the polynomial space, very good. Although we cannot like a ReLU, it's still for ReLU. For ReLU, you cannot reproduce polynomial beyond the degree 1, but you can approximate any order of the polynomial in a very high order of high accuracy. Okay. Because of that, of course, if you know the approximation theory, you have this one. You can, of course, you can get the result for the smooth function. Smooth function for the smooth component S, you can have a power to the S here. Of course, we can say if S bigger than D, then you have a no D. But this is not what we are. That's a very traditional kind of thing. You can get that. Okay. Okay. If another way is that why not? Why using ReLU? Why not using some other function? Okay, if you go a little bit step far, instead of using ReLU, you are given your freedom each time to choose between the ReLU and the floor function. Okay, floor function is essentially piecewise constant. ReLU is piecewise linear. If that basically each that easier your ReLU your network, then your approximation is wonderful. So what wonderful is because you can have, but let's forget about the continuous function. This is the Hulu function. We have this lambda n to the power of a square root L. So this shows also composition, power of the composition. Okay, your deep level, you have a deeper layer, you get lots of advantage for that. Okay, this you see. This is no D anymore. A D is here, but it's not important. You have here your power to L. Okay, this is very exciting, but we even you kind of get better for this second paper, but this is more or less like that. But people are not happy because people think, okay, your flow function, but flow function is okay. But people don't. Some people complain that the flow function is not good. It's a piecewise constant. So next exact results, I'm very excited. So the universal approximation for finite number of the neuron. Okay. Now I have a very simple computable activating function. So activation like that. Okay. So simple. Okay. From minus infinity to 0, you're using this. So this function, this is called soft sine function. Okay. From 0 to positive infinity, using this triangle wave function with period 2. This is a very simple function. You can compute. They're nothing complex. But with this function, what are the results? Okay, you get the same neural network. Neural network is the same as I said before. Only the activation function, you're using this activation function. Okay, this activation function. Then you have a hypothesis space. Basically, I need the hypothesis. You're given a width n, depth L. You generated this all the hypothesis. Okay, this is the hypothesis space with a fixed depth and L, fixed width. The results are exciting. You see the hypothesis space only have a finite neuron, okay, n times L neuron, which is dense in here. What does that mean? As long as L is bigger than 11, your n is bigger than n is neural work with this activating function is dense. That means, what do I mean dense? Dense means for aperture epsilon, for aperture f, for aperture epsilon, there is a f in this hypothesis space with finite number of neurons, such smaller than epsilon, for any epsilon. If you still think about the approximation rate in n and L, n is infinity. That means any rate you can imagine. Okay. So we can from this function we can generate a family of function. We have a theorem which can use the theorem here. One of them like that. This is the why I show this one, because I told you this is more like a signal. Calm, you switch on, you keep this function. This function also have the property. Only you need L is a little bit deep and N is a little bit big, but you still have a finite number neural using this as the activating function. You still have a density. Okay. Okay. Finally, I think I want to talk a little bit about this classification. I understand. You understand? Okay. Deep learning. One of the successful example for deep learning are classification problem. Okay. Let's start with a simple one. Binary classification. For the binary classification, you have a fx. Okay, fx equal to, essentially you can say binary classification is fx. You have a two class. One is the cat, one is the dog. Okay, the omega 0 is a cat set. Omega 1 is a dog set. Then you basically classification is you want to see all the x belong to omega 0. You need to be 0. All the x you belong to the omega 1. It should be 1. You look at that, that's back to my early points. For this kind of function itself looks very simple. You have two values, 0 and 1. If you want to have a cut in the range, you just epsilon smaller than half, you're done. It's very simple. But the problem is that your level set is very complex. It's a level set problem. Okay, your level set omega 0 and omega 1. You think about image classification. Okay, it's in the black image. Okay, white black image. You have a in a 225 by 225 dimensional space, and you have a two omega 0 and omega 0. The two high dimension two manifold in the high dimension space. Okay, so it's a very complex for the level set. Okay. So what do we show that? We show that our this fx is in fact in our hypothesis space for the activating function we use. as long as the L is bigger than this one and N is bigger than that. And you have a condition, omega 0, omega 1 have to satisfy this condition. But this is not like a unreasonable condition, because if you have these two sets, their closure are not empty, I don't think any classifier can really make a good classification. Okay, so you need the two sets, your closure at no intersection. Then my this function will be in here. That means for classification, if you're using this network, you don't have an approximation error. You only need to work on the generalization error and optimization error. Your function is in there, in your hypothesis space. I don't know your net is big, but in the normally your people doing classification, your network is much bigger than this number. L is much deep and N also much wide. So this is for L such that fx is that for any x, in that, they exist fine as equal to that. This is the I think I like this result. This means for this one I already said that you don't have approximation error, you only have a class. This also kind of generalize to the M class, not just for 2 class. Yeah, M class is the same thing. You can have the same result. This is our new paper. I think I'm very excited. You can find that one in my web page. To summarize, you want to estimate the error for your learning. Doesn't matter which task your error for learning. Normally you have three errors. One is approximation error, one is the generalization error, which is essentially error between the models, and another is optimization errors. And this talk, we give the estimate for the approximation error, like residual nets, or the network by ReLU, or the network by our special aggravating function. But then some of them error can be arbitrarily small. Some of them we have a rate of summation. So but what we do here, we don't need the data. We do the analysis, but we say what we only tell you is there exists such a function in your hypothesis space for your given neural network and given the width and depth and aggravating function. But we don't tell you how to get it. Normally deep learning, you go to the minimization, then you have other 2 errors. Some people, especially people doing classical approximation, they like to, why not I have an algorithm directly go to the approximator? The approximator maybe is not your best, but is bound above with some below by your best, bound above by some constant over your best approximation. So you still can do that. But this is a good question. There's many classical approximation people doing that. They directly have an algorithm together to find this one. But deep learning, you not go this path. And you want to go to this path, you remember this one. This is a very high dimensional approximation. I don't know how to directly find out. In fact, my proof, if you look at the proof, every proof is constructive. But constructive under constant assumption you have an F. Not that you have a data. I don't, not like a traditional kind of do the interpolation or whatever. You cannot do that. It's not, does not work the same. At least deep learning, the people doing this way, doing the minimization are doing this way. I think I finished here. Thank you. Thank you, everyone.